Okay, this is Pure Book 1, Chapter 2.5, the discriminant. Okay, if we solve a quadratic equation, we often use the full formula for solving it. And we'll find this thing under the square root has to be positive to give us two actual answers. And we see them on the graph here and here, or here and here, when we plot the graph of f of x, the full quadratic. And that happens when the discriminant is positive. Now we don't need to solve the equation to find the discriminant. We can just pick off a, b, and c from our function and insert them into b squared minus 4a times c. Similarly, when we look at the discriminant, if we get the value of exactly 0, x can only take one value. So we say that f of x has one repeated root, or just one root. We can see the roots on the graph because it's where we cross the x-axis, and in this case we are just going to touch the x-axis. And in fact, that root represents the turning point of the quadratic, or the maximum or minimum point. Finally, you might get asked about a quadratic equation where the discriminant is negative, is less than 0. And if we think about it, square rooting a negative doesn't give us any kind of sensible answer. So we say we have no real roots. And real is an important word here because there are roots, they just happen to be complex roots. So we can see this by seeing that our maximum or minimum point does not quite reach the x-axis, and we don't cross the x-axis at all. So there is no value that equals 0. Okay, so the simplest examples will just expect you to find out how many roots a quadratic function has, in which case you're starting with b squared minus 4ac. You are substituting in the values for a, b, and c, making sure you use brackets if b is negative, but also a and c. You need to be very conscious of the signs of all of the coefficients. So when we crunch the numbers, we come out with a negative number. And so the negative number tells us that we have no real roots. Once again, we're given a quadratic, only this time we notice we're not given an actual value for k, but that's for c, we're given k, but that's okay because we're given this information that we have one repeated root, which gives us the fact that b squared minus 4ac must equal 0. If we substitute in our values for a, b, and c, we get an equation where only k is unknown, and we solve for k. Finally, the most difficult type is when we have a quadratic equation, a quadratic inequality formed. This time the piece of information is we have two distinct real roots. This tells us that we have the inequality greater than 0, positive values. So we take our values of a, b, and c and put them into our formula for the discriminant. This time it's worth noting that p plus 3 forms an entire value for c. We must put brackets around it, and we're going to expand in just a second. So if we expand 4 into our bracket with the negative, we turn the 12 turns negative, so there's a potential error there, be warned. Then we can factorize that quadratic fairly easily, and solving quadratic inequalities is nicely done with a sketch if you get the numbers right. So the values of p equals 0, excuse me, p equals 6 and p equals -2 give us our roots. They look like this. We're interested when this quadratic, the blue quadratic, is greater than 0, and that happens when the y values are greater. So that is when p is less than 2, the p coordinates are less than 2, or greater than 6.